Hello and welcome to another video from our series on our YouTube channel Think Design Work Smart. I'm Bolboaca and I'm coming to you from the Mozaic Works studios, as always in the past 6 months. We have spent the last 6 months making interviews with a lot of interesting people, and we thought about creating a series of videos in which we discuss a few of the things that we learned. Perhaps you aren't patient enough to watch the whole conversations, although I would highly encourage you to do so because they are very, very interesting. But I believe it's quite interesting what we've learned. And the first thing that I'd like to discuss is this difference between class-oriented and object-oriented programming. But let me start from the beginning. We had a few interesting people being interviewed that were part of the initial stages of object-oriented programming. We had Joe Yoder, Wirfs-Brock, and Rebecca Wirfs-Brock. The last video that was published was with Rebecca. And all these three people gave us interesting insights about what object-oriented programming was supposed to be. And they didn't tell us specifically how object-oriented programming has changed and how it's done differently now. But there were bits and pieces that I extracted from the conversations with them. And I found this very interesting. So in a nutshell, what we see is that today many of the programming languages, or at least for a while, many of the programming languages that were mainstream, like Java, C++, and C#, they were doing something closer to class-oriented programming. And I remember when I started learning object-oriented programming that every book that I was learning would start discussing about classes and the relationship between classes, the relationship of encapsulation, polymorphism, inheritance, without paying a lot of attention to the objects. And this is a fundamental difference between what was, at least for a while, and what was initially object-oriented programming. And I'm being very careful here because I've noticed that many of the newer programming languages place more focus on objects, and many of the modern languages that we use today, like Groovy or Python or Ruby, it's much closer to the idea of objects and classes are less interesting there. But in languages like C++, classes are still very interesting, or Java or C#. But let's go back a bit and let's see what we've learned from these people. Wirfs-Brock was a very interesting person to interview because he was a pioneer in personal computing and object-oriented programming. He was really inspired by Alan Kay's vision, and if you don't know that, Alan Kay's vision was related to personal computing, was related to creating a computer that he called Dynabook that would be available to people to learn and interact and so on. But in order to build that computer, you need a few things. You need a graphical user interface, you need a mouse, and these are innovations that came out of Xerox PARC where Alan Kay was located. But more than that, you needed another way of designing software. Until this time period, what we had for designing software were functions or subroutines called back then. And subroutines, the idea was that you would have subroutines that work on specific data sets. If you think of languages like COBOL or Fortran, and perhaps I will be a bit wrong here, but the fundamental idea is that there was a some kind of coupling between the data structures that were used and the functions that were using them. But you could have a data structure that was kind of a database, and then have different functions using the same data structure. And if you imagine this growing over time, at some point in time, you realize that you don't know anymore which functions use which data structure and where are the dependencies. And therefore an idea emerged, which is, how about we combine functions with the data structures? So we encapsulate the functions with the data structures, and this is an object. Let's call it an object, for the lack of a better term. And so this solves a big problem, because now you can have the data structure with all the functions that relate to that data structure, and everything is clearer. You know where to look for the functions that modify or work with specific data structures. So this is one reason for having objects, and the reason being, when software grows large enough, you can no longer maintain this idea of data separated from functions in an easy manner, or at least you couldn't back then with the programming languages and the technologies that were available. And then there was another thing. So if you want user interfaces, what you need is a kind of thing that can live somewhere and that waits for events or for messages, and who responds to messages and returns, does something perhaps, and perhaps returns something. And this is a second thing that is important about objects, is that objects are created for specific goals, like UI. UI is a perfect case for objects where, once again, you have a specific object that lives there and that answers to certain calls. And so you have this idea of objects that encapsulate functions and data, plus the idea of messaging. Objects that send messages to one another and that respond to messages, and they kind of stay there and wait for messages. This also relates to another problem. If you are doing simulations, you have two types of simulations. One type of simulation is based on formulas. Like if you are doing something that is a physical simulation, you have a very clear formula. Mechanical simulation, part of game engines or things like that, you have a clear formula, and that can be encapsulated in a function, because basically what you have is you have some data, you apply a formula, and you get the new state of the system, for example. But there is another type of simulation. And the second type of simulation is the one where you don't have a formula, but you have something that is closer to, or at least what I understand, is a complex system. If you think about something like the weather, a weather simulation, one way you could do that is by having an object that deals with the wind, an object that deals with clouds, or multiple objects for each cloud formation, for rain, and so on. And then based on certain messages that get passed, so let's say, for example, temperature drops in a certain part of the atmosphere, and this leads to a temperature drop in a certain cloud, and this leads perhaps to rain, which may lead to increase in the wind speed, and so on and so forth. So these are things that kind of happen inside, but you don't have a formula to define what is the next state based on the existing state. It's more of something where you can model each of the separate objects and send messages to them and then those objects send messages to other objects, and so on and so forth, until you end up with a new state for your simulation and you can watch it unfold. So this is another factor for doing simulations. This is another factor for using object-oriented programming and using objects. And so then it was very interesting to realize this when discussing with Alan, and there are parts of the conversation, if you look at myself listening to Alan, I start realizing things, and it's getting very, very interesting. And then something else struck me when I was discussing with Rebecca Wirfs-Brock. Rebecca Wirfs-Brock is one of the pioneers of object-oriented programming. She worked with Alan Wirfs-Brock at Tektronix, the company that built Smalltalk. They were doing something else, but they decided to also try Smalltalk for their products. And she was very interested in making these objects work, and she tried to learn and switch her mindset from functional decomposition of a program into objectual decomposition of programs. And back then there weren't rules, so they had to figure out these rules as they moved on. But they had a very interesting system, which is Smalltalk. And Smalltalk has a very special characteristic, which I didn't realize how influential it could have been. But discussing with Rebecca, it turns out that Smalltalk had this idea of living objects. So Smalltalk has a virtual machine image, and you start that image, but once you start that image, you also get a bunch of objects that instantiate and kind of live in that system. It's like a world of objects, and objects live there. And then what you can do is to write your own objects and kind of interact with the existing objects. And I didn't quite get how this was happening back then and how advanced the tooling was and all that. But it seems to me that this is quite different from the way we are developing software now, because it's much more natural, much more organic. You are basically living in a world, you are creating new objects in that world, you are watching them interact with other things, and of course you focus on one or two or your own objects, but they may end up interacting with each other. And it's quite interesting because we are often missing this dynamic connection, this dynamic way of seeing programs run when we do software today. Of course, we compensate. We compensate by writing tests. We compensate by doing test-driven development or things like this. But perhaps there's something to be said about this world of objects and this natural, organic way of interacting and of seeing those objects interact. And perhaps we can have, once again, tooling like that, because today, imagine something like Spring Boot, which anyway has a dependency injection framework, so you could inject all the dependencies there. You start your Spring Boot application, those objects are instantiated, but then you go and start not only writing the code, but already seeing the interactions between the code that you write and the other objects. So this was very, very interesting to me, and perhaps we can learn something from this. And by the way, Rebecca told me that they were writing tests, but because they were doing this kind of interactive and dynamic type of development, they usually wrote tests afterwards. And anyway, the practice of test-driven development was not yet defined. So they were creating these objects. All the objects were tested, but the tests were usually written after the fact. And so here's the interesting part. Everything I talked about until now shows much more focus towards objects and much less focus towards classes. Objects were first. These people, these pioneers, were writing objects. They were trying to figure out how to make complex programs work, complex simulations, and so on, by having objects interact with each other. But classes came later, and classes were more like a facility. Once you have objects that look kind of the same, perhaps it's useful to have a class that, makes those objects, that classify those objects into one thing, so that you don't have to rewrite the same things again and again. And I imagine the same things happened with inheritance. Inheritance is a way of removing duplication, because you could write the same type of object again and again that has a few similar things, but then different things. And one way of dealing with that is by using inheritance. But now the problem with inheritance is that inheritance becomes a very strong relationship. And so you need to be very careful of using inheritance in your code. And by discussing this problem with Rebecca, she told me that, of course, they wouldn't imagine very deep hierarchies. And inheritance was mostly useful in case you're building a framework, and not so useful if you're building an application or a product. And you had to pay a lot of attention to when to use inheritance and to avoid having these relationships other than in very specific situations. Another interesting thing that came up is about thinking dynamically, thinking about the behavior of your objects. So there are basically two ways of designing objects. One way is to start from the data that you want to have in your system, split that data into smaller parts. There was back then already the database ideas were around, and so you could apply the same ideas to programs and say, we have this data, we split the data, and these are our objects, and design your objects based on the data that they encapsulate. However, it was interesting that Rebecca realized, and she didn't tell me that, but I believe that part of it was her experience with living objects. She realized that if you think differently, if you think about behaviors of the objects, your design looks different. And therefore, she came up with something called responsibility-driven development, which is, by the way, the first DD type of technique that appeared in software development. And responsibility-driven development has a lot to do with looking at behaviors, looking at how objects behave instead of the data they contain. And now, I'm not sure whether there's one of them is better than the other, but they are very different approaches. So perhaps there are situations in which data-oriented, data-driven design makes more sense, and there are situations in which behavior-driven design makes more sense, or responsibility-driven design. And by the way, the ideas from responsibility-driven design were then used into other techniques like test-driven development, where we say we write tests on behaviors. So a behavior is a similar thing, and actually kind of the same thing with the responsibility. Behavior-driven development comes from the same idea. You look at behaviors, which are, in a way, responsibilities. And so that should be a good idea to look at when you want to improve the way you design code using objects. All right, so class-oriented versus object-oriented programming. Class-oriented is something that I believe has been done by C++, by Java, by C#. A lot of focus on classes, a lot of focus on what you can do with classes. However, the fundamental idea here is that classes are fundamentally classifications of objects. And the best way to classify objects is to think about the objects first and then figure out which objects are similar and make sense to be in the same class, or make sense to be in an inheritance relationship between classes. And I didn't realize this difference until very late in my career, because all the books I was reading and all the advice I was getting about object-oriented programming was basically about classes and wasn't about objects. Only later on I realized that objects are more important. And by discussing with these people like Alan, Rebecca, and Joe Yoder, I realized that, look, in fact, objects are, yes, much more important. And to end here, it was very interesting to discuss with Rebecca the state of object-oriented advice in the modern times. And I asked her about the various types of advice that I often hear from people related to objects. Favor composition over inheritance. And she basically said that yes, you should pay a lot of attention. I mean, you should not completely avoid inheritance, but use inheritance where it makes sense. And don't go into very deep hierarchies of objects, because that will be very, very hard to understand, very, very hard to maintain. So if you have deep hierarchies of objects, perhaps you're better off of restructuring those to composition. Another big question that I asked her was, how about solid principles? And her answer was that solid principles are quite confusing, and that the ideas behind solid principles are covered in the classic principles of low coupling, high cohesion, but also that one thing you can do is, instead of looking at solid principles as principles that limit the things that you can do, you can look at constructive ideas that allow you to construct an object graph, an object hierarchy. And in order to do so, the best way is to increase your design vocabulary. So she didn't say all that in these words, but this is what I understood from our conversation. So that's it. These are a few things that I've learned by discussing with pioneers of object-oriented programming. And I really wanted to make a short video that explains these things, and I hope you'll find this useful. So if you are interested, I hope I piqued your interest now, and perhaps you have more time or more interest now. You can go back and look at our interviews with Joe Yoder, Alan Wirfs-Brock, and Rebecca Wirfs-Brock. They are full of of bits of wisdom and of historical pearls that we often forget in software development. We often believe that we are the first generation of programmers, and we forget learning from the past and from the experiences of people who have been there when computing was just started. So I invite you to watch these interviews and these conversations, and until next time, remember to think, design, and work smart.